All right, so get this. We're going deep today into a sequence that's so simple. It's almost like sneaky, just alternating ones and twos forever. But trust me, there's way more to this than you'd think. We're looking at entry A000034 from the Online Encyclopedia of Integer Sequences, the OEIS, a total gold mine for number nerds like us.
Yeah, and what's fascinating about the sequence is how it really shows the deceptive depth of math, like a chameleon blending into different areas and revealing these unexpected connections.
So let's break it down. We're talking about the sequence 1, 2, 1, 2, and so on. The formula to generate it is pretty straightforward. It's A of n equals 1 plus n mod 2.
Right, where mod, that's the modulo operation, basically gives you the remainder after division. So if n is even, n mod 2 is 0 and you get 1. If n is odd, n mod 2 is 1 and you get 2. Simple, right? But hold on. Things are about to get interesting.
Okay, I'm intrigued. What's the first, aha moment here underneath this really basic pattern?
Well, this sequence, it also represents the base 3 digital root of n plus 1. A digital root is just what you get when you keep adding the digits of a number until you're left with a single digit.
So if you start with 13, you add 1 plus 3 and get 4. That's the digital root in base 10. But what about in base 3?
In base 3, 13 is written as 111, which is 3 squared plus 3 to the power 1 plus 3 to the power 0. Add those digits, 1 plus 1 plus 1, you get 3. But we're in base 3, so that reduces to 1.
Okay, so the base 3 digital root of 14, which is 13 plus 1, is 1. And this pattern just keeps going, matching our 1, 2, 1, 2 sequence. I'm starting to see these hidden depths.
And we're just getting started. Now get this. Our sequence, it's also connected to something called continued fractions.
Continued fractions. Those sound kind of intimidating.
They might look complex at first, but they're really quite elegant. Imagine fractions, like nested inside of fractions, kind of like those Russian dolls. Turns out, our simple 1, 2, 1, 2 sequence, it represents the continued fraction 4, the square root of 3 plus 1 divided by 2.
Wait, so this basic sequence can be used to approximate a value. That involves the square root of 3. Okay, my mind is officially blown.
And there's more. This sequence also has something called a Hankel transform. Without getting too technical, think of it as a mathematical tool that reveals hidden patterns in sequences.
So what is this Hankel transform? Tell us about our sequence.
Well, the Hankel transform of our sequence is a very specific pattern. 1, -3, 0, 0, 0, and all the rest are zeros. This suggests our simple 1, 2, 1, 2 pattern has some unexpected complexity lurking beneath the surface. It's like discovering that a seemingly simple melody actually has a complex structure underneath.
Wow, I would never have guessed that. This is getting more and more interesting. What else is hiding in this sequence?
Well, you might be surprised to know that it's also the, quote, lexicographically earliest sequence with a very specific property. Lexicographically just means in dictionary order. And this is the very first sequence in that order where you can't fit a polynomial of a certain degree to a certain number of consecutive terms.
So it's kind of like a rule breaker.
Yeah.
When it comes to fitting certain math curves to it.
Exactly. It has this unique characteristic that sets it apart from other sequences. And just when you thought we'd covered it all, we find ourselves stepping into set theory with something called maximum antichains.
Okay, set theory always makes me a little nervous.
Antichains are sets where no two elements are related in a specific order. Imagine a group of people where no one is the boss of anyone else and the number of maximum antichains. In the power set of 1, 2, Han, that's the set of all possible subsets, actually follows our 1, 2, 1, 2 sequence.
So we've got digital roots, continued fractions, Hankel transforms, lexicographical ordering, and now set theory. This simple sequence is like a mathematical octopus, reaching its tentacles into all sorts of areas.
And there's even more to uncover. What's really fascinating is that this one sequence can be described by a whole bunch of different formulas. Each formula provides a different lens, through which to understand its properties.
It's like having multiple maps to the same destination, each one highlighting different landmarks along the way. Tell me more about these formulas.
Yeah, it's like having a whole toolbox, with each tool revealing something different. About the sequence, for instance, one formula uses exponents, a of n equals 2 raised to the power of the quantity 1 minus -1 to the power of n, all divided by 2.
Whoa, that looks a bit complicated. Can you break that down?
It's actually pretty elegant when you think about it. You see, -1 raised to an even power always equals 1, and -1 to an odd power always equals -1. So if n is even, the whole exponent becomes 0, and anything to the power of 0 is 1. If n is odd, the exponent becomes 1, and 2 to the power 1 is 2.
Oh, I see. It's like a mathematical light switch, toggling between 1 and 2, based on whether n is even or odd. That's neat.
Exactly. And then there's another formula that uses the greatest common divisor. A of n equals GCD of n minus 1, comma n plus 1.
Okay, remind me. What's the greatest common divisor again?
It's the largest number that divides two given numbers without leaving a remainder. So if you have 12 and 18, their greatest common divisor is 6.
Right. So how does this tie back to our sequence?
Well, think about it. If n is even, then both n minus 1 and n plus 1 are odd, and their greatest common divisor will be 1. But if n is odd, then n minus 1 and n plus 1 are even, and their greatest common divisor will be 2.
So the greatest common divisor acts like a filter, picking out either a 1 or a 2, depending on whether n is even or odd. That's a clever way to generate the sequence.
It really is, and this connection to divisibility hints at deeper relationships between the sequence and this fascinating world of number theory.
So we're seeing these links to different areas of math, but what about real-world applications? Where does this sequence actually show up, outside of, like, theoretical mathematics?
One area is combinatorial game theory. The study of games like NIM or Whitehoff's game. These are strategy games where players take turns removing objects from piles according to certain rules.
Oh, right, those games. That can really make your brain twist.
Exactly. And it turns out that our sequence, with its unique properties related to things like maximum anti-chains, can actually be used to analyze winning strategies in some of these games.
So if I study the sequence, I could become a combinatorial game champion. I like where this is going.
It might give you an edge, but beyond game theory, there are also connections to number theory, group theory, which deals with algebraic structures, and even to fractal sequences, those infinitely self-similar patterns found in things like snowflakes and coastlines.
Our little sequence
is
popping up in some pretty unexpected places. It's like it's woven into the fabric of math itself.
That's a great way to put it. And that's what makes this deep dive so compelling. It's a reminder that math isn't just a collection of isolated formulas and theorems. It's a beautifully interconnected web of ideas. And exploring those connections can lead to some truly amazing discoveries.
Speaking of discoveries, you mentioned earlier that one of the formulas for our sequence connects to the Collatz conjecture. That's one of those big unsolved math mysteries, right?
Yes. The Collatz conjecture is a fascinating problem that has stumped mathematicians for decades. It involves repeatedly applying a simple rule to any positive integer. If the number is even, you divide it by 2. If it's odd, you multiply by 3 and add 1.
I remember hearing about this. The conjecture states that no matter what number you start with, you'll always eventually end up at 1. Sounds simple, but no one's been able to prove or disprove it.
Exactly. And what's intriguing is that one of the formulas for our sequence, A of n equals, if n equals 0, then 1. Otherwise, if mod of A of n minus 1, comma, 2 equals 0, then A of n minus 1 divided by 2. Otherwise, the quantity 3 times A of n minus 1 plus 1, all divided by 2, actually incorporates that same rule from the Collatz conjecture.
Wait, really? So could our seemingly simple sequence hold the key to cracking this math enigma?
It's certainly a possibility. While no direct link has been established, the fact that this formula appears in connection with our sequence raises some tantalizing questions. It's as if this sequence is dropping little breadcrumbs, inviting us to follow a trail deeper into the mathematical forest.
This is incredible. I'm starting to understand why mathematicians get so passionate about these seemingly abstract concepts. There's a real sense of mystery and discovery here.
Absolutely. It's all about the thrill of exploration, uncovering hidden patterns, connecting seemingly like disparate ideas. And in the case of this sequence, the journey is far from over.
Okay, I'm hooked. What other surprises does the sequence have in store for us?
Well, in the final part of our deep dive, we'll take a closer look at some of the other fascinating formulas and explore what they reveal about the nature of this curious sequence. Who knows? We might even stumble upon a few more unexpected connections along the way.
I can't wait. Let's take a quick break, and then we'll jump right back in to the fascinating world of sequence A00000034. Okay, and we're back, ready to wrap up our exploration of sequence A00000034. I gotta say, this seemingly simple sequence has really opened up a whole new world of math ideas for me.
It's amazing how something so basic can have so much depth and connect to so many different areas of math. It's a great example of how appearances can be deceiving in mathematics.
Absolutely. So let's dig into some of those other formulas we talked about earlier. Each one seems to offer a unique perspective on this 1-2-1-2 pattern.
You got it. Let's start with that one using exponents. A of n equals 2 to the power of, the one is negative 1 to the power of n, all divided by 2. It might look a bit intimidating, but it's really quite elegant.
Yeah, I'm ready for a challenge. Break it down for me.
Remember how negative 1 raised to an even power always equals 1, and negative 1 to an odd power equals negative 1? Well, this formula cleverly uses that. If n is even, the whole exponent becomes 0, and anything to the power 0 is just 1. But if n is odd, the exponent becomes 1, and 2 to the power of 1 is 2.
Ah, that's how it generates the patterns, like a seesaw, going up and down between 1 and 2.
Exactly. Now let's look at the formula. That uses the greatest common divisor. A of n equals GCD of n minus 1, comma, n plus 1. This one highlights the sequence's connection to divisibility.
Okay, I'm following. So how does the greatest common divisor fit in?
If n is even, then both n minus 1 and n plus 1 are odd, and the greatest common divisor of two odd numbers is always 1. But if n is odd, then n minus 1 and n plus 1 are both even, and their greatest common divisor will be 2.
So the greatest common divisor acts like a sieve, separating out the 1s and 2s, based on whether n is even or odd?
Precisely. And this connection to divisibility hints at a deeper relationship between this sequence and the principles of number theory.
It's incredible how a single sequence can be expressed in so many ways, each one showing us something new.
It speaks to the interconnectedness of mathematics. There are often many paths to the same truth, and each path can highlight different aspects.
And speaking of interconnectedness, there is that formula that referenced another sequence, A of n equals A000034 of n divided by 3. I'm curious about this one. What's the story there?
This formula is like a bridge, connecting our sequence to a whole other world of mathematical ideas. Sequence A010704 is interesting on its own. It's related to the number of ways to express a number as a sum of consecutive integer.
Wait, so our simple 1-2-1-2 sequence is
Yep.
somehow related to the ways you can add up consecutive numbers. That's wild.
It is pretty mind-blowing. While the exact connection might require some more digging, it suggests there's more to this story than we might think. It's like a secret passageway to a new wing of the mathematical mansion.
Exploring these sequences is like going on a treasure hunt. You never know what you might find.
That's a great analogy. It's all about being curious and following those mathematical breadcrumbs.
Well, I think we've done a good job unpacking this unassuming sequence. We went from its basic definition to its connections, to digital roots, continued fractions, Hankel transforms, set theory, and even the Collat's conjecture.
We've seen how its different formulas provide different ways to see its properties, revealing connections to divisibility, number theory, and other fascinating sequences. It's been quite a journey.
I'm a little sad our deep dive is ending, but I'm walking away with a new appreciation for the hidden depths and unexpected connections that are underneath even the simplest math ideas.
That's the beauty of math. It's a world of endless exploration and discovery, and sometimes the most unassuming concepts can lead to the most profound insights.
I couldn't agree more. So to all our listeners out there, I want to leave you with this thought. With all the formulas, connections, and applications we've talked about, what other secrets might this sequence be hiding? What other parts of math might it connect to? The possibilities are endless.
Remember, even the simplest ideas can spark incredible journeys of mathematical exploration. So stay curious, keep asking questions, and you never know what you might find.
That's it for this deep dive. We'll see you next time as we explore another fascinating corner of the mathematical universe.
Until then,
Happy exploring.